All right, so welcome. We're going to be talking about induction, in particular, weak induction, not strong induction. And so, what I have here is I have an example of like kind of like a canonical example of summation that we're actually trying to prove. And so, anytime we're starting out with induction, what we want to do is we have a two-step process. One, we're going to have a basis step, right? Okay, in which we prove that it is the case for the smallest possible value. Okay, and then after that, we're going to have our induction portion of the proof. And in the induction portion of the proof, what we're going to be doing is we're going to be showing that if we assume that our statement is true for k amount, then we show that in fact it'll be true for k plus 1. Okay, and basically the idea here is that if I show that it's true for the first one, okay, and then if I show that it's true for k of them, then that would mean that it's now true for 2. Or excuse me, if I show it for k plus 1, then it's true for 2. And then 2 becomes the first one, and then we know that it's true for k plus 1, so it's true for 3, and so on and so on and so forth. And that actually tells me, right, okay, that in fact it'll be true for any n. So let's say, for example, I want to prove 1 cubed plus 2 cubed plus all the way up to n cubed is equal to n times n plus 1 divided by 2 squared for some positive integer n. Asking this for some positive integer n, and since it's positive, we're going to be starting at 1. So that's going to actually be our basis step. All right, so we've got this thing, it's called the basis step, and we're going to denote this statement right here, prove, or just this statement, excuse me, 1, not the proof part, but just the 1 plus 2 cubed all the way out to n times n plus 1 divided by 2 squared, okay, as p of k. Okay, so our basis step is show p of 1 is true. And that's fairly simple. All we're going to do in order to show that p of 1 is true is we're just simply going to state, we're going to plug in 1 into the equation and show that the two sides are actually equal. So 1 cubed, okay, which equals 1. All right, let's see if that's actually equal to 1 times 1 plus 1, okay, divided by 2 squared. Okay, well, that's simply 2 divided by 2 squared, which equals 1. So p of 1 is true. So what we've done is we've actually shown our basis step. Now what we have is we're gonna have the statement. So now we need to actually deal with the inductive step. And in the inductive step, what we're going to do is we're going to first assume that p of k is true. So we're going to assume that p of k is true. So that means, so k cubed plus k, k, so 1 cubed plus 2 cubed plus k cubed is going to equal k times k plus 1 divided by 2 squared. So we're going to assume that that's true. We don't need to assume that with any kind of proof. We're just going to say, okay, let's assume that that's true. All right. What we want to do is we want to prove that p of k plus 1 is true. Specifically, that 1 cubed plus 2 cubed plus k cubed plus k plus 1 cubed equals k plus 1 times k plus 1 plus 1, or k plus 2, divided by 2 squared. Okay, so basically that if I plug in, instead of k, I plug in k plus 1 into the summation, what I end up with is I still end up with a true statement. All right, so we're going to start with the left-hand side of the equation. Anytime we do any kind of proving where we've got, basically we're using equations, start with the left-hand side. okay, and then go towards proving towards the right-hand side. So we'll say, all right, so 1 cubed plus 2 cubed plus k cubed, all right, plus k plus 1 cubed, okay? Now that's going to end up equaling, all right, what you want to notice here is that this thing here is in fact, by assumption, okay, is k times k plus 1 over 2 squared, right? We already said that that was true. P of k is true. This is P of k. This is P of k. So we know that this thing here is equal to k times k plus 1 divided by 2 squared plus our k plus 1 cubed. Okay? Generally, when you're doing these kind of induction proofs, that's what you're going to do. You're going to basically take your assumption step, right, and replace it into the inductive part of your proof, right, and then show that the two sides are in fact going to end up being equal. Now this statement, we're going to move down to here. This is going to then equal, okay, k squared times k plus 1 squared plus divided by 4 plus k plus 1 cubed. Now, a trick that I've learned by doing a lot of induction proofs is to notice that we have a common factor. That is a k plus 1 squared that I can actually take out of both. And I'm also, in fact, in this case, I'm going to pull out a 1/4. So this is going to be 1/4, and this will be, excuse me. No, I'm just going to pull out the k plus 1 squared, right, times k squared, okay, plus, and we're going to be left over with a k plus 1. But this is k squared over 4, by the way, plus k plus 1. Now this is then going to equal, now I'm going to pull out my 1/4. So I'm now going to have 1/4 k plus 1 squared times, and this is now k squared plus 4k plus 1, plus 4, excuse me. Okay? Now notice that's a perfect square trinomial. So this is going to be equal to 1/4 times k plus 1 squared times k plus 2 squared. Okay? Now, over time, you get kind of used to, oh, that looks an awful lot like what I'm looking for. In fact, if I look up here, remember how I wrote this out? I wrote it out right here. That's the form that I'm looking for. Okay? And I remember this, k plus 1 plus 1, that's actually k plus 2. There it is. I've actually now got exactly what I need. Okay? Because what I can do now is this is going to then equal, okay, I'm going to pull everything into the squared. So this is now going to be k plus 1, okay, times k plus 1 plus 1, right? That's your k plus 2, divided by 2, and then all of it squared. Okay? And so p of k plus 1 is true. Is true. Consequently, now that we've done the basis step and we've done our inductive step, we can actually say, you know what? If I know that the first one's true, then I know each subsequent one's true because I just kind of like build each one up, right? It's kind of like this ladder process, and so it tells me that it's true for all n. So what I do is I'm just to finish my inductive proof, I'm going to say, and so p of n is true for all positive integers n. And our proof is finished. All right, so that's induction in a nutshell. Okay, let's review it. Let's review it then. Every inductive proof is going to begin with a basis step. That is that you're going to prove it for the smallest value within its range. In this case, it was the positive integer n, and so consequently, we'll start with 1 because 0 is not positive, right? So what we do then in our basis step is show that p of 1, our statement p, is true. Okay. Basically plug it in. That shows that p of 1 is true. The second part is the inductive step. And inside of the inductive step, what we're going to do is we're simply going to make the statement, right? We're going to assume that P of K is true. So like if we have a random value K, we're going to assume that P of K is true, okay? And I generally will write out exactly what it means for P of K to be true. Then we're going to go in and essentially we're going to attempt to prove equality of some sort or another by utilizing that P of K is true. In this case, for this kind of proof, what we did was we replaced the first K elements with P of K because they were equivalent, and then we went on to just simply show that P of K plus 1 is true. So the inductive step is to assume that P of K is true, and then to show that P of K plus 1 is true. Once we've done that, the basis step combined with our inductive step tells us that our statement is in fact true by mathematical induction.